In this class, I will cover these three topics: free fall, and then we will talk about mass and weight. Now, free fall means any object, if I take this object and I just drop it, it is called free fall. So, free fall means a body falling under the force of gravity only. When I drop this object, what are the forces acting onto it? The gravity. We are ignoring the air resistance. So the only force acting onto it is gravity. So free fall is fall of a body and the only force acting on the body is gravitational force. Okay. Now when a body is falling freely, what about its speed? Will it be falling with constant speed? No, because there is a force of gravity. We have done Newton's first law, then Newton's second law. We defined force F is equal to ma. We saw that whenever a force acts on a body, the speed and direction may change. In this particular case, it is moving down in the same direction, but its speed will keep on changing. If I have dropped it, its speed, what is the direction of the gravitational force? Downward. The body is moving in the direction of force. So whenever force is applied in the direction of motion, the speed increases. So for a free fall also, the speed will keep on increasing. And this is the expression from where we can calculate the acceleration of freely falling body. And whenever a body is falling freely, its acceleration, we call it gravitational acceleration, and use a symbol G for it. Gravitational acceleration. So gravitational acceleration means the acceleration of a body which is due to the gravitational force. Every force can cause acceleration. The acceleration which is caused by the gravitational force is called gravitational acceleration, and we use symbol G for it. Though even now the expression is same. So F is equal to mg if the force is gravitational force. Okay, we can calculate its value. So for a freely falling body, the speed is changing, speed is increasing due to the force of gravity. And now we have done Newton's law. So if this is the body and which is falling, I drop an object of mass m, it is falling towards the earth. What is the force acting between them? We can calculate using Newton's law of gravitation. How much is that force? G m1 m2 by r square. m1 means mass of earth, m2 means mass of this object, divided by the distance square. So I have to take, if this is the radius of earth, then distance between them is this. But this is almost RE, because RE is 6400 kilometer, 6400 kilometer, nearly, roughly. This is the value of radius of earth. So in comparison to this, taking the same example where I dropped the object, it is falling by a distance of around 2 meters. So 2 meters is negligible in comparison to 6400,000 meters. So I can take this distance of the object which has been dropped from the center of earth as r only. So RE square. This is the distance between the object and the center of the earth. So this is the force using Newton's law of gravitation. Now from here, this is the force. So what will be the gravitational acceleration? This is F upon m, mass of this object. We are calculating the acceleration of this. This is the force acting on this. So 1 upon m into what is the force? G me m upon re square. M gets cancelled. So g me upon re square. This is the value of gravitational acceleration for Earth particularly, but we can calculate it for any planet. So see now, in the gravitational acceleration we are getting the mass of Earth, we are getting radius of Earth. So gravitational acceleration is independent of the mass of the body that has been dropped. It does not depend on that. It depends only on the mass of the planet and the radius of the planet. I have assumed here that the shape of Earth is spherical. So this is the acceleration. This is how we can calculate any acceleration. Acceleration means force upon mass. Force is g m1 m2 by r square divided by the mass of this object. We are calculating the acceleration of this. So force onto this divided by mass of this particular object. Force on this is by Earth, this one, divided by the mass. So g m e upon r square. Now if I substitute these values, G is GME upon R square. RE is 6400 kilometer. So it becomes 6.4 into 10 raised to the power 3 kilometer. It is also 6.4 into 10 raised to the power 6 meters. And mass of Earth is around 6 into 10 raised to the power 24 kg. And G 6.67 into 10 raised to the power minus 11 Newton meter square per kilogram square. If I substitute all these values, G comes out to be 9.8 meter per second square. So this is the value of gravitational acceleration on Earth's surface. Now in higher classes you will study that this value of gravitational acceleration depends on many other factors. But roughly 9.8 is the value that can be taken for all practical purposes. But if the distance from the Earth's surface is increased, force will reduce, so the gravity will reduce. Similar way, if we include the rotational of Earth, even then the value of G will be affected. So G changes, it depends on many factors. But right now, it's sufficient to know that the value of gravitational acceleration is roughly 9.8 meter per second square. Now what does it mean? 9.8 meter per second square. So G is 9.8 meter per second square. This is the value of gravitational acceleration. Or I can write 9.8 meter per second per second. I explained you earlier also what does it mean. 9.8 meter per second square means, and this is constant. So constant acceleration means the speed of freely falling body will increase by 9.8 after every second. So if I drop it, so at t is equal to 0, the velocity is 0. I have the object in my hand, I am dropping it. Whenever an object is dropped, it means initial velocity is 0. So t is equal to. What about this? Now the speed will be 9.8 meter per second. At 2 seconds, v will be 9.8 will be added into it. So 9.8 plus 9.8. So 19.6 meters per second. And same way, now 9.8 plus 9.8 plus 9.8, this will be the answer. And same way. So after every second, the speed will increase by 9.8. So constant acceleration means this only. Constant acceleration means the change in velocity is constant. So when an object is dropped, we call it that it is falling freely, because the only force acting onto it is gravity. And whenever a force acts on the body, the speed does not remain constant. We can calculate the acceleration or the change in speed by using Newton's law of gravitation. It tells us what is the force acting on the object divided by mass. This will give us the acceleration. For Earth, it is this. And now, Just see whether this value is same for all planets or will it be different. See, the value of gravitational acceleration is depending on the mass of the planet and radius of the planet. So if I take an object on moon, if I drop an object on moon, the change in speed after every 1 second will not be 9.8. It will be different because mass is different, radius is different for moon. The value of g, roughly if I take moon, it is about 1/6 of it. 1/6 of 9.8. So change in velocity will be very less after every second. So the speed with which the object will strike the moon surface will be much less than the speed with which it strikes the earth's surface. So gravity is very less on moon. And one very important consequence of it, it is because of less gravitational force on moon, that there is no atmosphere there. The pull required to hold the atmospheric gases, that is very less. That's why the gases escape and there is no atmosphere. Now I am giving you some examples of free fall. Suppose I fill this with water, this is glass, and I drop it. Filling completely filled with water and then I drop it. Just imagine, water will come out of the glass or not during its fall. It will not actually. Why? This glass is falling freely, the acceleration is 9.8. Water inside is also coming down with an acceleration of 9.8 meter per second square. So they are both falling with same acceleration. The change in speed after every movement is same for both. So both of them falling freely, water as well as glass. It will not pour outside. Another example, weighing machine. When we stand on it, it shows our weight. Okay, we press it and then the pointer moves. Now, telling you one experiment which you should imagine, don't try. If I stand onto it and tie this machine on my feet, and then I jump from some height, say from a table to the ground. This weighing balance tied to my feet and then I jump. What will be the reading of this? Just imagine. See, you are falling freely and this object is kept on this, and if both of them falling freely, it is coming down with an acceleration of 9.8, my hand is also coming down with an acceleration of 9.8. So actually it is not pressing against it. They are in contact but nothing more than that. It's not pressing against it. So the weighing machine will show zero weight. Okay. So these are few examples for free fall. Now mass and weight. Mass we have studied in junior classes also. Mass is a measure of total contents of the body. It is measured in kilogram. You know, if I take this object, the total contents of this box, that is the mass of this object. It is denoted by M, and SI unit is kilogram. Other units may be gram and many other units, quintal, that is also. Now, unit of weight and unit of mass. First I will tell you the difference between the two and then conclude which is a unit of mass and which one is a unit of weight. Kilogram, gram, units of mass. Weight is actually the gravitational force. On any object. So if an object of mass m is kept on Earth, mass of this object is m, weight of this object is g MEM upon RE square. So weight of any object is the gravitational force with which Earth pulls us. That is the gravitational force, and we have just done that. This is actually g, so I can write it mg. So whenever we are calculating weight of an object, weight is Newton's second law we can apply, m into a, and a is the gravitational acceleration. So weight of any object is m into g. Mass, again take the same example. Mass means the contents, so that will remain same. Even if I take it on moon or any other planet, mass will always be same. What about the weight? Weight will change. Weight means the force with which the planet will attract it. On Earth, it will be mg. On moon, it will be mass into gravitational acceleration on moon, which is 1/6. So weight of any object on moon will be 1/6 of its weight on Earth's surface. Weight will change because weight depends on the gravitational pull of that planet, and that in turn depends on mass and radius of that. But mass does not depend on anything. So mass will remain constant for any object, but weight will depend on. Now how do we measure weight? Weight is force. So what is the unit of force? We have already done it. Newton. Newton is a unit of force. And sometimes while measuring weight, when we say my weight is 70 kg, 50 kg, what does it mean? Actually, kg is not a unit of weight. Kg is a unit of mass. So what do we mean when we say my weight is 50 kg? It is actually 50 kg weight. This is another unit of weight. Kilogram weight means weight equal to 50 into 9.8 in Newton. So 1 kilogram weight means 9.8 Newton. So for any object, whatever is the mass, suppose mass is 10 kg, we can say it's very 10 kg weight. It means in order to calculate it in Newton, 10 kg needs to be multiplied by 9.8. Otherwise 10 kg weight, that is okay. This is also one unit of, and this is what we mean when we say 70 kilogram. Actually it means 70 kilogram weight. So to calculate it in SI unit, we need to multiply it by 9.8. So 70 kilogram mass means 70 into 9.8. That will be in Newton. So that is what we mean by weight. Weight always depends on the mass and radius of that particular planet. It will depend on many other factors also that you will do in higher classes. I may give you one or two examples. Suppose I keep a duster on my, okay. If I move it down and then I take it up and I am changing the speed of my hand, then it does not appear equally happy in both the cases. If I bring my hands down, it appears lighter, but when I take it up, it appears heavier. And if I move my hands with an acceleration of 9.8, freely falling, I gave you that example, I keep this over it and let them fall. So there will be weightlessness. Free fall is a state of weightlessness. Weight becomes zero in free fall because it is not pressing against it. Okay, so it is weightlessness. So if I bring my hands downward with an acceleration of 9.8, zero weight. If I move it down with different acceleration, it appears less. If I move it up, it appears heavier. And if I move my hands downward with an acceleration more than 9.8, what will happen? More than 9.8, it will lose contact because it is free to fall. So it can fall down with an acceleration of 9.8, but I am moving my hand with an acceleration more than 9.8. So it will lose contact. So it means the acceleration of my hand is more than 9.8. But anyway, all these things you will study in higher classes. Here it is sufficient to know that acceleration on Earth's surface is 9.8 and weight of any object is mass into gravitational acceleration. So that's all in this topic. Thank you.